That's good. Hey there, guys. I really love that intro song. It's so good. Yeah, okay, comment your names. We need to do a quick register. So, Ollie, where are you on my list? You're not here. What? No, there he is. Cool. Ollie is here. Grace is here. Jasmine standing by. Yeah, like it. Where's Jasmine? There you are. Jake is here. Melissa there. Harry. Oh yeah, Harry's in the other group. Cool. You guys going surfing again? Molly is here. Poppy, hey Poppy, you missed the other stream, but it's good to see you today. Emerald, yep. Jack, where are you at, Jack? There you are. Ed. Jolie, you missed the other stream, so good to have you back. Rob, Roberto, Elizabeth, Dan. Dan, you missed yesterday, so it's good to have you back. All we're missing is Dom. Anyone seen Dom? Have I missed Dom in the register? No. Otherwise, full house. Nice to see you all. Hope everybody's well. No one's got it yet. Anyway, so today's plan is to kind of talk you through the difference between how you know if it's a binomial question or a normal question. Because it can be confusing. You just see some numbers and it's hard to work out what's what. So the way to tell the difference then is with a binomial, you always have a number of trials, but you could have a number of trials in this one as well. The difference is you could have numbers in both of these. Oh, Jolie, I hope you're alright. I hope it's not too bad. Yeah, so both of these could have a number of trials. In binomial, always has a number of trials. Normal could have a number if we're talking about a sample mean hypothesis test. The difference is what the number actually relates to. So in binomial, a number of trials is like a number of things. It's like 5 things do this. What's the probability 10 things win 10 trials do this? In normal, the number is how many data points you've got. So it's like there are 5 objects and the mean of them is this. So with binomial, the trials or the number relates to a fixed probability. It's to do with a number of successes or items. Whereas with normal, the number relates to like the size of the variable. So yeah, anything you do in normals is relating to the actual the value of a variable, whereas binomial it's a number of wins. So always number of wins or number of trials. This one's more talking about what the actual values of variables actually are. Okay, when should you use Z then? Well, if you got mu is 0, sigma is 1, you use Z. Or if you're trying to find mu or sigma, you have to use Z. Anything else, you can just use a calculator. When should you use a normal approximation to binomial? If you see the words use a suitable approximation, that's when you do your normal approximation bit that we did on Tuesday. Cool. All right. It's worth saying last lecture was pretty awful because I think things were breaking and I had hiccups and it was a nightmare. So I did that lecture again yesterday, period 2. So lecture 2 yesterday. It's up on YouTube. It's a much better take of the same lecture. So if you want to watch that instead, you might get some more out of it. But yeah, just so you know that one's there. Okie dokie. So today, the plan for today is just to try a mix of normal questions, binomial questions, and ones that combine both, just to kind of like consolidate everything we've done so far. And the main thing today is trying to pick out what method you should use for each bit. So just to get you kind of warmed up, we're gonna actually, before we do this one, I think there's one we didn't finish off on Wednesday that I'd like to start with. As soon as it loads. Oh, cool. Come on, machine. There we go. Cool. A2 starter, yeah. So I'd like you guys to start with this one today, so you didn't get around to it last lecture. Come on. There we go. Cool. Yeah. Everything's frozen. Come on. Come on. Cool. Okay, so you got machine. Let's move this down a bit. Machine filling packets of sugar. Why is it so slow? Come on. Yeah, cool. Right, there we go. So a machine fills 1 kilogram packets of sugar. The actual weight of sugar delivered to each packet can be assumed to be normally distributed. Cool. All right, so the manufacturer requires that the mean weight of the packets is 1,010 grams, and 95% of all packets can stay between those two. So show this equivalent to demanding the variance. So we've got to find the variance of part A. So find sigma, and we do that using a Z distribution. Okay, and then after that, we're doing a normal hypothesis test. So could you guys give this one a go? It's worth 7 marks. I'll give you 7 minutes. Comment if you need any help. Yeah, and we'll go through it in 7 minutes time. Cool. Right, get started, guys. Ollie, what's the problem? Oh, Dom, cool. I'll take you off the register. Why haven't you watched the lectures, Dan? They're all online on YouTube for you to watch. How about right now, just go back, watch the other ones, and then see if you can log into this one later. I'm doing this lecture again in an hour and a half. So, yeah, I'll do this again at 10 past 1. So if you, right now, log off this one, go to the channel, look at yesterday morning's lecture or Tuesday's lecture, catch up, and then come back in later, because otherwise this won't make any sense to you. Ollie, so part 1, we're doing a standardized normal distribution. So that's one where if you sketch it, we're trying to use 0.2, 95% of the packets are between 1000 and 1020 with a Z distribution on the calculator to find Z, then use that to find sigma using Z equals X minus mu over sigma. So you're using, in order to do it. But yeah, Dan, I would go watch the other stream because you know you're gonna have gaps otherwise. There's no need to have gaps when you can catch up and just watch this one in exactly 2 hours time. Okay, Dom, yeah, Z is the standardized normal distribution. Remember, it's the distribution that has a mean of 0 and a standard deviation of 1. So it's the distribution that all other distributions kind of get modeled to fit. It's the way your calculator works out any of these probabilities. So Z is the standardized normal distribution. B is a two-tailed test because it could either be filling them too much or filling them too little. So yeah, two-tailed test then, Melissa. Right, last minute, guys, and then we'll go through it. Cool. All right, guys. So let's go through this. Okay, so part one. Machine fills 1 kilogram packets of sugar. The actual weight can be assumed to be normally distributed. The manufacturer requires these conditions. What was that saying? Yeah, cool. Okay, so we're told that 95% of all the packets filled by the machine are between 1000 and 1020. Yeah, Elizabeth, that's fine. So, mean is 1010. Lower is 1000. Upper 1020. And we're told that these areas are each 5%. Oh, sorry, 95% is the middle, so these are each 0.025. Okay, so we need to find out. Well, we can just use either of these ones. It doesn't really matter which. We'll take 10,000. We'll do the lower one. So we'll do 1,000. We're going to find the z value that corresponds to these values here. So we're going to try and find whatever z is down here, and whatever z is here. And we can use, yeah, I mean, I'm happy for you guys to go watch the other lectures, but you could have done that at any point between then and now. So for today, yeah, but in future, you should really have already done this. But yeah, probably if you want to come back for the one later, I don't mind, that's fine. Okay, yeah, so if we find probability, put it in the calculator, find z, we're then going to use the equation z equals x minus mu over sigma in order to turn our z value, our x value, and our sigma back. Oh, actually, we're trying to find sigma. We know z, we know x, we know mu. Put all those in, and we can find our unknown sigma. So if I bring the calculator up, and we're doing inverse normal, we know the area if we do it to the do left hand tail. So the area is 0.025. Sigma is going to be 1 for a standardized distribution with z, and mu is going to be 0 for z. And that's why z is useful, because it always has a distribution of 0 and 1. Then we can just do the coding. So if we execute that, we get minus 1.96. So that's our value down there. Okay, so what we're going to do is put that z into the coding here. So we got z even is 1.96. That can go in here. X is the value we know, so the value for this one is 1000 over there, and mu is 1010. So let's put all that together. So minus 1.96 equals 1000 minus 1010 divided by sigma. And if we rearrange that, how do I know it's inverse normal? Inverse normal is when you've got the probability and you're trying to find the value. So we got this bit and we want to try and find this bit. So rearrange that and we're going to get sigma equals, so type this into the calculator, 1000 minus 1010 divided by minus 1.96. And we get sigma is 5.1. So they've asked for sigma squared. So if I square my answer, I do get 26. Square that, 26.3. Right, any questions about this? So yeah, Ollie said, how do you know it's a inverse normal? It's always inverse when you know the probability, so you know the area, and you want to find the value. NCD is when you know the value and you want to find the area. So inverse is knowing the area, wanting to find the value. And it's always a Z distribution when you're trying to find mean or you're trying to find the standard deviation. Cool. Right, so that's the first bit. The second bit is a hypothesis test for this. So, yeah. Oh, what am I doing? There you go. Right, so test at the 2% level. So, okay, we've got a sample of 8 packets chosen at random. So we need to write down our distribution of sampled means. So we got our X with a bar on it for means. It is normally distributed. We're assuming that the mean is the same, so 1010. But the standard deviation now will be 26.03 divided by the number of values we've got. So we've got 8 in our sample. Cool. Okay, so we're going to use a 2% significance level for our test. So we're going to state our null and our alternate hypotheses. So the null hypothesis is always that nothing's changed. So we're going to say mu equals 1, 0, 1, 0. If we read through, basically we're trying to decide if the machine is not fulfilling condition I. And condition I was just the mean is this. So if it's not fulfilling that, we're trying to say the mean is, we're testing if the mean is not 1010 anymore. Right, so we kind of draw our distribution. We're trying to find the two critical values for, it's a 2% significance level, so we're splitting that between each. So we've got 0.01 probability for that one and 0.01 probability for that one, because we split the 2% between each tail. And we're going to try and find out what these two critical values are. So if we find these, we're going to see if the test statistic, which we'll find in a minute from these weights, is within these values or whether it's a critical value. So bring back the calculator. And we're doing inverse again with a tail. Well, we need to do left and right. So inverse normal. We'll do tail to the left first with an area of 0.01. Sigma is square root of 26.03 divided by 8. I mean, you'd square root all of that because it was the variance over 8 that we had. And then the mean is 1010. So if we execute that, we get our critical region for the lower tail is 1005.8. So that's this value here. Our upper value, well, all I need to do, because the probability is the same, on the graphical calculator, all I need to do is change that to right. If you're doing on a class whiz, you'd need to change your probability now to being 0.99 because the class whiz only does less thans. And we get 1014.2. Cool. Okay, so we just need to find out whether our value lies in that critical region. And to do that, we need to know what the mean is of our sample. So we just need to work out what the mean is of all of these numbers that you can see on the screen. Let's get myself out of the way. So we're going to do this on the calculator. Here's one I did earlier. So I've typed all the numbers in the first column here. I'm then going to tell the calculator that my frequencies are 1, which they are. And then we're going to do a one variable stats analysis. So we get the mean of our sample is 1013. So sample mean 1013.4. Is that critical? So let's have a look. Sorry, what are you saying? How and wide did I get? Well, we got two tails to test. You've got the lower tail. We now need to test for the upper tail as well. So if you want to find the upper tail, either type it in with the tail to the right, or you can use the class whiz and put the probability as 0.99. And that's our upper critical region. So our sample mean is 1013.4, which is in between those two, so it's not critical. So we can assume that our machine is okay. So not critical. So accept H1, and then it sounds like the machine is okay. I've run out of space. You probably wouldn't write the machine is okay in the exam. You'd say there is evidence to suggest that the machine is fulfilling condition 1. Cool. All right. Hopefully you're all okay with that. If there's any more questions, please ask now. And then we're going to move on to a couple more that I prepared. So just doing questions and examples today. All right, let's go then. So it's going to clear that so it's ready for later. As soon as this leads, yeah, I saw early. That's interesting. Cool. All right. Gonna leave. Done. Save as draft. Yeah, BBC News said. Come on, is this done yet? Have I crashed it? Yeah, okay, good. All right. So, cool. All right, here we go. So, yeah, daily mean temperature in Hern. So this is a nice, easy one. It's just a hypothesis test. 4 marks. I'm gonna give you guys 4 minutes to try it yourselves. Um, there you go. 4 minutes on the timer. Comment if you need help, and comment when you've got your answers, and we'll see who gets it first. Cool. Good luck. Cool. Right, guys. Hopefully you found that okay. Let's go through it. So daily mean temperature, standard deviation 2.3. So let's call it T for temperature. Is normal. 2.3 is our standard deviation, and the mean, if we read down, is going to be 12. Okay, so that is our population. We've got a sample though, so our sample means it's going to be 12, and the standard deviation, no, 2.3 squared, isn't it? 2.3 squared over 20, which is our sample. So we get this. All right, so we got sampled. The mean of the sample is 11.1. We're testing at the 5% significance level whether the temperatures should be less than 12. So we need to state our hypotheses clearly. So H0, the mean is still 12. H1, we're trying to test if it's less. So mu is less than 12. So we've got a one-tailed test for our mean here. We know 12 there, we're trying to test D to the left. So we know this area here is 0.05, and we're trying to find out what this critical value is here. So bring the calculator up. Distribution, normal distribution, inv, tail to the left, area 0.05, sigma is, as I said, 2.3 over 20, or 2.3 over root 20. Two 2.3 divided by root 20. And mu is 12. So hit 12, execute, and we get 11.15 is our critical value. Okay, so the mean of the sample is 11.1. So 11.1 is critical. If you look at the graph, 11.1 comes up below 11. So it is in the critical region. So it does mean we reject the null hypothesis. So 11.1 is less than 11.15. Therefore critical. Therefore accept H1. The mean is less than 12. Again, I've not got much space, so I'm kind of abbreviating. You want to say, accept H1, reject H0. There is evidence to suggest that the mean is less than 12, or the mean temperature is less than 12. So really link it back to the question and make it clear what your conclusion is. Right, anyone got any questions? Everyone okay? Cool. All right, next slide. So we're going to do one about rattlesnakes, which is quite a nice question. What I want you guys to do in this one is, first of all, just to read through it, and without doing it, I'm going to give you 3 minutes to decide, there's 3 parts, A, B, C, and D, what each part is actually asking you to do. So what kind of a question are we dealing with? Normal, binomial, mix of both, hypothesis test. So just identifying what each bit is to start with. So we'll set the timer up for 3 minutes. Just try and work out what it's going to be asking you, and then we'll do it in a minute. Cool. All right. So what do you guys reckon? Could you please comment what you think each bit of the question is asking for? So what's part A, what's part B, what's part C, and what's part D? Just so I get a little bit of feedback from how you guys find things so far. So what is each bit asking you to do? Ollie, not sure. Come on, Ollie. Go back and watch the other videos if you're not sure. Anybody? All right, let's go through it. Please, can you guys go back and watch the other videos if you find this difficult? Because I know lots of you are away for 2 of these. Go through it. If you still need help, ask me over the weekend, and we can do a Teams chat. But you should be getting this by now. Other groups fine with this, so go over it. I think it's because of the absences that some of you are struggling a bit. So part A, we're told 5% of rattlesnakes have a length less than this. Find the mean length. So we're trying to find the mean. If you need to find the mean, as I said back at the beginning of the lecture, if you want to find the mean, you need to use a Z distribution. The mean is unknown. We need to use Z. So, not the cat's one. Where's the snake's one? There you go. Cool. Nope. Cool. Right. So yeah, we need to use a mean distribution to find. We need to use the Z distribution. So Z. What should we use? L. And we're going to use the Z distribution to find mu. Let's just do it because we can, the quicker we get through it, the more questions I can get you guys to do in the lesson. So we'll go through this one. So we're going to use a Z distribution in order to find the mean. So if I do a sketch, 5%, so standard deviation 0.4, we don't know where the mean is, that's what we want to try and find. 5% of rattlesnakes have a length less than 1.7. So this area here is 5%. So we're going to find the Z value that corresponds to 5%, and then we're going to use Z equals X minus mu over sigma and rearrange it to find mu. So if we bring back the calculator, it's going to be inverse normal because we know the probability and we want to find the value. So I'm going to put in 5%, 0.05. Oops. 0.05 there. The sigma, standard deviation, we know is going to be 1 for a standard normal, and mu is 0 for a standardized normal. So click on execute, and that finds us the Z value. So the Z value corresponding to 1.7 is minus 1.645. All right, so we're going to uncode that using our Z equation, Z equals X minus mu over sigma. So minus 1.645 is equal to X, which is 1.7, minus mu, which we don't know, divided by the standard deviation, which was 0.4. If we times up by 0.4 and then add mu and subtract the number, we can find that mu equals 2.358. So that's the mean for our sample, or the mean for our distribution. So I can write down all the information from the question as L is approximated by a normal distribution with a mean of 2.358 and a standard deviation of 0.4. Oops. Let's move that back down. So 0.4. Cool. All right, so now we're ready to do the rest of it. So part B, 10 snakes are chosen at random. So 10 chosen at random, that's a number of things. It's already sounding like a binomial. Find the probability at least six, so it's definitely a binomial question. So we want to do binomial. So X is a binomial distribution. We've got 10 in our sample. But we don't know the probability. So we're going to need to find that probability using a normal. So, got to do a normal distribution so that we can find the probability we need for our binomial distribution. So, for the normal then, we're trying to find the probability that x is greater than 2.3, or that the length is greater than 2.3. So, if I plot it, we're going to do an NCD because we know all the stuff now. We know the mean, we know the standard deviation. We're going to find the probability that L is greater than 2.3. That probability is going to be the probability we use for our binomial. And then we're asked to do the binomial. The probability x is at least 6, as it says here. So bring back calculator. This time it's going to be an NCD, normal NCD. Lower value is going to be 2.3. Upper value, put something big in. Sigma 0.4. I should have written squared actually earlier. That should be squared. And the mean is 2.358. Cool. So that gives me a probability of 0.5576. And that is the probability that we're going to use for our binomial. So if I write that into the binomial, 0.5576 in there. And we're going to basically do this part of the question now. So back to the calculator. Distribution, binomial, BCD. Lower is going to be 6. Upper, well, there's only 10 in our sample, so upper is going to be 10. And the number of trials is 10. And my probability of success is 0.5576. So we get the probability is 0.5241. Or 55242 if we're rounding to 4 decimal places. So that should be our answer to part B. Right, has anyone got any questions at this stage? Because I've gone quite fast through the first 2 bits. So we needed to find the mean. So we used the Z distribution. We found the Z values and we coded them to find the X values. And part B, we did basically what we're doing last year. The only problem was we didn't know the probability of success. So we used a normal, which you can see above me, to find the probability of success, which we then used in a binomial distribution to find the probability of greater than or equal to 6 successful trials. Okay, anyone got any questions? Because the next bit's going to be the hypothesis test. Right, let's clear this. All right, so adult rattlesnakes are a length m. So, okay, we've got a new distribution now. And m is also normally distributed, and it's got a standard deviation of 0.3. Right, if we read further down the question, so we're looking at a hypothesis test, and we think that the mean is 1.9. So we're going to put that in, and that's going to be the thing that we're testing. So there's our normal distribution for the length of female rattlesnakes. Okay, given a random sample of 20 is taken. So we're now talking about our sample mean distribution. So mean distribution, normal, mean is the same, 1.9, and the standard deviation, 0.3 squared over 20. All right, and we're testing at the 5% level, so we're trying to find these critical regions again. So we do a sketch. On the sketch, then we can put our 5% region. So we're trying to test if the mean length is not equal to this. So it's going to be a two-tailed test. We're going to have 0.025 up here and 0.025 down here. We need to state a hypothesis. Let's do that down here. H0 mu is 1.9. H1 mu is not 1.9. Cool. All right, so we're going to do our test. We're going to find the critical values, and then we're going to compare them in part D. So if you bring back the calculator, two tails, so we need to find two different critical regions. And we know the probabilities, so it's going to be an inverse normal. So push inv, and then tail 0.025. Sigma is going to be 0.3 divided by square root of 20. And my mean is going to be 1.9. So we get our inverse normal value there is going to be 1.77, which is my first critical region. And we're going to do the same thing. So on class Wiz, you'd want to change your probability to 1 minus 0.025. And on the graphical, we can just change the tail to right. And we should get 2.031. Or 2.03, we'll say there. Okay, so those are my critical regions. So critical M mean is less than 1.77, it's critical. Or if the mean is greater than 2.03, it's also critical. Right, so that's our part C done. If you look at part D, the length is found to be 2.09. Okay, is that critical? Well, if we look at our graph, the critical region is 2.03. So 2.09 is going to be in the critical region. So we can say 2.09, if I get rid of the calculator, is greater than 2.03. Therefore, critical. Dom, central. I've not used central before. I think it's when you know the middle of the data, but it's rare that you do that. It would only be if you had a completely symmetrical distribution, which we never will. So ignore that, just do tail as left and right. So yeah, it's critical, it's in the critical region. Therefore, we reject H1, accept H0. And our conclusion is that the mean of female rattlesnakes is likely to be longer than 1.9. Cool. Right. Anyone got any questions about this one? Again, it kind of covers everything. Anyone? Okay, we've got quite a lot of time actually today, so I'm going to give you guys a bit more time for the next question. We're going to have a look at this one about a fleet of vans. So if I move this down a little bit. There we go. So a company has a fleet of identical vans. Let's get me out of the way. Their policy is replace. Should I make this a bit bigger? It's kind of small. Should we accept H1? Yes, I think I said that, didn't I? Ah, I've written the wrong thing, haven't I? Sorry. Thank you, Grace. I think I said accept H1 and wrote. Yeah, it is critical. So critical, reject H0, accept H1. Thank you for spotting that, Grace. Yeah, it is in the critical region. Where did 2.09 come from? 2.09 is the length they gave us up here. So they found the mean was 2.09. 2.09 is in our critical region, therefore we reject the fact the mean is the same and accept the fact that the mean is likely to be bigger than the 1.9 they stated here. Any other questions on this before we move on to the van question? No? Right, I'm going to try and move it on. Okay, so, no, it's moved again. Damn it. So a company has a fleet of identical vans, blah, blah, blah. So the variable X is the number of miles driven before they need to replace these tires. Okay. X is normally distributed with a mean of 27500 and a standard deviation of 4000. So part 1 is just a simple sketch normal, find the probability. Part 2 is a binomial distribution. Part 3 is a inverse normal, and then part 4 and part 5 is a hypothesis test. So could you guys try this? I know it looks like loads of marks, but this is from the old A level where they didn't have graphical calculators. They didn't have any calculators that could do this. You have to get a table out for all of it. So if you guys give this a try, I will give you, I think, 12 minutes. So please comment if you need help, because 12 minutes of just sitting there is going to be a waste of time. But give it a go. This shouldn't be too hard, but comment if you need help, or comment if you get a correct answer, or if you think you got a correct answer as well. So timer starts now. Anyone need any help? No one's really commenting. Come on, guys. Any help or any answers? Please shout. Answer part 2 should be 0.259, I think. Is that right? No, that's a different question. Oh, I've deleted my workings for this one. What? Why have I done that? Oh no, that is right. 0.259. Cool, Grace, let's have a look. Yep. And what's your part 3 answer in reference to? Oh, yep, I agree. So far, so good. Excellent. It means greater than. Yep. Do you guys want a couple more minutes to finish it off? Or should we just start going through it? Let's start. We'll slowly go through it. Right, so it's cold in it. We've got a group of identical vans. Yep, blah blah blah. So we're going to write down distribution. So they told us to use x. So x normal 2750. Actually, let's save some space. X is normal 27500 and sigma is 4000. Cool. All right. So we want to find the probability that x is greater than 25,000. So we do that just on the calculator. It's pretty easy. So we're looking for a probability. So we're doing a NCD, dist norm NCD. Our lower value is 25,000. Upper value, put in something huge. Sigma 4000. Oops, and mu 27500. Cool. If you solve that, you get 0.747340. Ah, 747340. Cool. Everyone right with that so far? Right, part B then. So now we're looking at binomial. So 10 vans in the fleet are selected at random. So we've got a binomial distribution now. N is 10, we're selecting 10. And we want the probability that tires on 7 of them. So we're looking for probability x equals 7, which we haven't done in a while. And the probability we need is the probability that the tires last longer than 25,000 miles. If you look up, that's what we just did in part A. So we know the probability is going to be 0.734. So we can just do this on the binomial part of the calculator. Sorry guys. There's a calculator. Bring up the binomial distribution to dist binomial. We know the x value, we want to find the probability, so it's going to be a, b, c, d. Actually, it's probability x equals 7. So it's going to be bpd, because we know the percentage. So x is 7, number of trials is 10, p is 0.734. It equals, there you go, 0.25259. So 0.259. Cool. Everyone keeping up? Now we're on to part 3. So tires of 99% of the vans last more than k miles. Find k. So let's do a sketch for this one. Do it in red. So 99% of the mile of the tires last for longer than this value. So most of the data is above. So we got 0.99 of the data's there. And we're trying to find out what is this k value here. So because we know the probability, it's going to be an inverse function. So back to the calculator. We've got distribution, normal distribution, and inverse. So inverse normal. Tail, you could do it either way. You could do right 0.99, left 0.01. Because it's on right, let's keep it there. So 0.99 for 99%. And everything else is already there because we're doing the same question we were before. So we get k equals 18194.6. Like that. Okay, so that's the basic bits done. Right, rest of it is a hypothesis test. So wait a couple. I'll wait 20 seconds or something and see if any of you guys need any help with that. Then we'll get rid of it, scroll up, and attempt this hypothesis test. So has anyone got any questions leading up to now? So we had standard normal or a basic question, normal mixed with binomial, and then an inverse normal question. Right, so let's make some space. And let's move it all up. Cool. All right, so a tire supplier claims that different type of tire will have greater mean lifetime. Okay. So we're trying to test if our tires have improved. So let's okay. We need the mean from earlier. So our sample mean then x bar is going to be a binomial with the same mean as earlier, 27500, and our standard deviation 4,000 squared, but we need to divide it by the sample size. So a random sample of 15 vans. So there's our sample. So this is what I was saying earlier. The 15 vans are vans with a mean with an actual value. So we're talking about the number of miles driven for each of these vans. It's not just a number, it relates to something real. So we're trying to find, so first of all, suitable null and alternative hypotheses. So H1, the mean is the same, 27500. Alternate hypothesis is mean is, and then read back through it. They're claiming it will have a greater lifetime, so we're trying to test if the mean has increased. Okay, so that's part 4. Part 5 then. So we're doing the test at the 5% level. So we're trying to see if it's increased. So we're going to do, oops, wrong place. This here is 5%. We want to find this critical region and see if the test statistic, which they said is 28,630, is above this or below this. So inverse calculation on the calculator. We're going to put in our area as 0.05, our tail is to the right. Find out this value and then see if it's significant or not. So inverse normal to the right, area 0.05. Sigma is going to be 4,000 divided by square root of 15. And mu is the same. So work it out. I typed in something wrong because that doesn't look very correct. That's infinity. Area, I put 0. Okay. 0.05. Cool. Okay, there we go. So our value comes out critical region as 29198.8. So 29,198 miles. How many miles did we do on our new tires? 28630. Ooh. So that is not critical. That is less than the critical region. Therefore, not critical. Therefore, reject H1, accept H0. There is no evidence. The tires are better. You can't see that, can you? Cool. Anyone got any questions about this one? So again, kind of samey. Once you've got these skills, they're easy questions. It's just being able to read them and know which bit is asking you which bit. Cool. Got 13 minutes left. That probably is time to get one more done, I reckon. Just so I can go through a few things with you guys, make sure you're doing the assignments and the skills checks. Work through them at your own pace, but I would try and get loads done over the Easter break so that you're ready. We got basically, I reckon, two lectures left of stats after this. Should you always have one decimal place at the end of the values found using the inverse normal e the miles? Can do. I mean, looking at the question, they've got no decimal places there, so you probably could get away with rounding that up to 9.8 and say it's 199. That value is a whole number, so yeah, yeah, it's up to you really. I would look at the data, look at the sample mean they've given you, and see how many decimal places that's accurate to, and then you don't need that decimal place if theirs is like 5 sig figs, use yours as 5 sig figs, because you're only ever going to be comparing your critical region to the sample mean anyway, so kind of compare it. Yeah, it'll be the end of the syllabus after 2 lectures, and then we're going to be revising, so we'll probably start with going over pure, because obviously there's no videos for pure, whereas you guys can just, if you want to revise stats, watch it again. And I've been redoing first year stats with my first year, so those are there. Mechanics videos will be there with my further math students, so I'll probably start doing pure with you guys so that we can put all these videos up, and so you can just rewatch them and pick up stuff from that. The other one is over Easter, I will try and arrange a day where I can do a Teams chat with each of you individually to go over your mechanics tests and show you what you did wrong. So it'll probably be in the second week of Easter, but I will let you know more closer the time. But we will do like a, just so I can go over that with you guys and you can actually get some feedback on it, because if I mark it, you're not going to know what you did wrong unless you can actually see your work again. All right, 10 minutes left. Let's see if any of these are, that one's probably going to be a bit too big. Where's the cats one? They're all very samey, really. All right, let's try this one. We'll see how we do. We got 10 minutes. 3, 4, 5, 6, 7. 7 marks. 10 minutes. Yeah. I'll give you guys 5 minutes to try this, and then we'll go through it. So I'm cutting your time in half a bit, but it's so that we still have time to actually go through this. Right. So there's that. If you want to get started. Yeah. If you have any other questions, guys, just shout. Sorry, guys. All right, so part A is a binomial. It's pretty kind of straightforward binomial. So you got a random sample of 40. N is 40. The probability that it lasts longer than 500 hours is 0.52. So 40, 0.52, we're looking for greater than 22. So it's a binomial cumulative distribution, which you can see over here. So I'm going to type everything in and work it out. So our lower is going to be 22. Upper is going to be, how many are there? There are 40. So upper is going to be 40. Number of trials is 40. And the probability is 0.52. So we get 0.4133. For the first bit. Okay, second bit. What are the two conditions under which the normal may be used as an approximation to binomial? Well, there's two of those. If I type these up, n is large and p is close to 0.5. So you just need to learn those. There you go. Okay, and then this is where it gets a bit difficult in part C and part D. So, random sample of 250 components is taken, and 120 lasted longer than 500 hours. Okay. Assuming the engineer's claim to be correct, use a normal distribution to find the probability that 120 or fewer lasted longer than 500 hours. So we need to use a normal approximation. That's the key here. So remember our two equations were mu equals np, and sigma is the square root of np times 1 minus p. So let's start off by finding mu and sigma before we worry about anything else. So mu is going to be 250, which is our sample size, times our probability. Well, we're talking lasting longer than 500 hours, so that's still 0.52% as was claimed in the beginning. And sigma is going to be the square root of np, so 250 times 0.52 times 1 minus p, which is 0.48. So we can work out both of those numbers. I think we get sigma is 7.9 and mu is 130. So now we've got our binomial distribution. So x is now modeled as a normal with mu as 130 and sigma is 7.9. Cool. So we turned it into a normal distribution. But there's another thing we need to worry about. Remember, we've got to do a continuity correction. So we're trying to find the probability that 120 or fewer. So probability x is less than or equal to 120. We need to work out how to continuity correct that. Because remember, if I do a little sketch up here, we want it to be less than or equal to this one, 120. So we want to include all of this bar. Now the normal distribution won't do that. The normal distribution would cut it off at 120. So we want to go really from 120.5 so that we include all of the shaded area. So we're going to do on the calculator, probability x is less than or equal to 120.5. Remember, that's a continuity correction. So bring back the calculator. We're looking at normal now. So dist norm, we've got NCD. So lower is going to be 0. Upper is going to be 120.5 so that we include all that bar. Sigma is 7.9 and mu is 130. Hit equals and we get the probability is 0.11457. Or 0.1146, let's say. Okay, so we found that the probability 120 or fewer last more than that time is 0.1146. What did they say? They said they lasted longer than 500 hours. Okay, well, hang on. So we've got, what am I looking at? Let's get rid of all this. Sorry guys, I know this is a bit over time, but real quickly. So assuming they're correct, so they took a sample of 250 components and 120 of them lasted longer. So let's actually work that out. So 120 out of 250. 0.5. Yeah, okay, that's exactly what she said. We found it's only 11.46. Hang on. Use probability to find 120 or fewer last longer than 500 hours. Okay, so we found the probability to be, it's quite unlikely. 0.11 is the probability x is less than or equal to 120. So would you say that that's a good approximation? She said that 52% last longer. Based on that probability, the likeliness of our sample only having 120 last longer was really, really low. So I would say, there's an 11% chance of that happening if this number is true. So I would say the engineer's claim could be false. So engineer's claim could be false. There's only 11% chance. So if you had a 5% significance level, it would pass. If you had a 12% significance level, it would pass. I don't know, maybe 11% is okay. You could argue that either way. But you need to talk about that. So with her claim, 11%. Yeah, I guess if it's 5% sig level is what we normally talk about, that's all right. But yeah, cool. All right, that's it for today then, guys. We will come back to this after Easter. Let me know over Easter if you get stuck on anything, and please get through as many assignments as you can. All right, cheers. Bye.